Okay, so what we're going to cover real quick here is using feedback to improve SNR, and then basically the rest of the class we're going to use feedback in data converters and improve SNR using the feedback. And now the reason why we use the SNR is that you can just throw it up here if you want, Rob. Just throw it here. Is that it makes the input appear like it's Bennett's criteria. So let's fix that. So remember, if we just went to a single input VN and we went to an ADC, ADC, that this input has to be busy changing by greater than an LSB, etc., right? And when we use feedback, we can put in a DC input and still have the benefits of all that filtering that we talked about. And so I want to just throw a generic topology out here, which here's our analog input. And that goes in here. And then we'll go to a, we'll just keep it generic right now, some sort of transfer function A of F. And then an ADC, and just as a sanity check for myself, how do I model that ADC? Yeah, summing block with an addition of quantization noise, right? So here, this is analog, and this is digital. And then we come back around and we'll go to another filter, B of F, to a DAC. So this is all digital here. And then take the output here and subtract it. And so here, this is analog as well. Okay, so what I want to do is if you take, and let's just write, you know what, I'm going to rewrite this a little nicer with replacing this as a quantization block. I'm not, does the DAC introduce quantization noise? No, so when I write this transfer function, I'm going to have input, summer, A of F, then an addition of quantization noise, then B of F coming back in here on the next page. Okay, so let's do that and then derive the transfer function and talk about that. So we have our, what did I write, Vn, and then A of F going to a summation of VQE of F, and my output. One of the things that you need to think about here, because you might be thinking, why the heck would we do any of this? And the answer is because we're going from analog to digital, so it's a way to do analog to digital conversion. Okay, so we'll go back here, subtract that, so we can write that V out is equal to, the signal here is B V out. Oops, it should be minus, plus Vn times A of F plus VQE of F. Does anybody not follow that? Yay. And so I'm going to move the V outs on this side, and I'll get V out times 1 plus A of F times B of F is equal to A of F times Vn. Now I'm getting a little ahead of myself, plus VQE. Yes? Here I just moved V out, A, B to this side and then factored out the V. Yeah. Or I get V out of F equals A of F over 1 plus A of F times beta of F times Vn plus VQE of F all over 1 plus a of f, b of f. Now we need to talk about this because this is pretty useful. This term right here is commonly called the signal transfer function. Or STF, obviously why. There's our input signal, and that's the transfer function it undergoes. And this term here is called the noise transfer function because it's shaping the quantization noise. So let's just think about this for a moment. Knowing that V out is digital and all the requirements we have on VQE. So if I make A of F really big, okay, what happens to this term? Yeah, well, if A of F goes to infinity, for example, this term will go to, yeah, 1 over B, right? Does everybody agree with that? And if I make B 1, just a wire, then V out becomes, for this part, V in, and the signal transfer function is 1. So if I can make this term A of F really big, and I make B a wire, then this term becomes 1, and V in, which is analog, passes directly to the output. Now, if I look at this term, if B is a wire, as B is 1, and A is big, what happens to my quantization noise? Goes to 0. So now, when I implement these circuits in the future, I will use an integrator for this block here. The reason I use an integrator is that at low frequencies, the gain analog integrator ideally goes to infinity. Now you might ask, well, why don't I just use a really big gain for all frequencies? And the answer becomes you can't make the system stable. Because remember, it's nice, and with feedback, you get all these benefits like gain desensitivity, immunity to imperfections in the components. But the drawback of using feedback is you got stability you have to worry about. So if we use an integrator here at low frequencies, the input passes to the output, and the noise gets reduced. Now this is a key point because in all of these topologies that we talk about in this coming chapter, which will start in 2 seconds here after we're done here, we're effectively doing what's called noise shaping. If you look at this quantization noise where we had the ADC was represented as a noisy circuit block and the quantization noise was constant, we assume from DC to F sub S over 2. Okay? When we run that quantization noise through an integrator, we make the quantization noise at DC very small, but then the quantization noise at higher frequencies grows because the gain is smaller, right? Does everybody see that? So a simple example here, let's take this term here, and let's set on the next page, let's just use an analog integrator. So for an analog integrator, we'll not worry about the gain. What does A go to for an integrator? What does A go to for an integrator? Here, let's do it for digital integrator. What's a digital integrator? What does A go to? Yeah, let's say z to the minus 1 over 1 minus z to the minus 1. Does everybody agree with that? Just so you know, I'm going to pause on this because I expected everybody to scream what an analog integrator is. It's 1 over S. How do I prove that? Well, remember that z is e to the j 2 pi f over fs, which is approximately 1 plus j 2 pi f over fs for f much, much less than fs. Does everybody agree with that? Remember that? Okay, and so then if I plug in z to the minus 1 over 1 minus z to the minus 1, that's 1 over 1 minus z, which is, z minus 1, which is, using this approximation, 1 over s, where s is equal to j omega. And I'm not worrying about the gain here, which has a gain of f sub s, or what the gain of the integrator is. Does that make sense to anybody? Okay, one more example of an integrator. Here, this is an analog integrator. Here's V in, here's V out. The gain is V out over V in is the feedback minus 1 over j omega c divided by R, which is 1 over S times 1 over RC. Gain is 1 over RC. I don't want to spend time on this, but you should feel comfortable when someone says integrator to say 1 over S in the S domain, or z to the minus 1 for a delaying over 1 minus z to the minus 1. Okay, so I'm going to continue with the example now, but before I do, are there any questions? Okay, so I want to show you using these equations. I got a question. What's VQE of F? What is it? Yeah, it's the power spectral density of the quantization error, but what is it? I mean, what did we assume it was in this chapter? The power spectral density is VLSB squared over 12 times, yeah, 1 over F is S. Remember, it's a power spectral density. Units are volts squared per hertz, so it's the power per bandwidth. Any questions? Okay, so we'll come back to that in a moment. So let's rewrite this, where I'm going to say B is equal to 1, A is equal to z to the minus 1 over 1 minus z to the minus 1. Do we know how to implement this? Forget the gain for a moment, but do we know how to implement this in analog form? You guys are killing me. What's that? No, in analog form with op amps. Yeah, the discrete analog integrators. Remember in the end of chapter 2? Here, remember this? And then remember these equations here at the bottom of page 66? Right? You'll know that before long because we're going to be using them a lot. All right. So let's plug everything in here. And we get V out is equal to z to the minus 1 over 1 minus z to the minus 1 all over 1 plus z to the minus 1 over 1 minus z to the minus 1 times V in plus VQE divided by 1 plus z to the minus 1 over 1 minus z to the minus 1. Anybody disagree? All right. And then we do a little algebra here, and that gives us V out equals z to the minus 1 times V in. My output is my input just delayed by 1 clock cycle, plus 1 minus z to the minus 1 times VQE of F. And we can put F here to be more exact. Okay, here's where I cringe. What is this? Yeah, a differentiator. So does everybody agree that if I put my input signal into that circuit, now keep in mind this isn't theoretical. We're going to make simulations and build actual circuits in the simulations on this stuff. The input goes to the output with 1 clock delay, and then I differentiate the quantization noise. So let's show, okay, well, even a simpler question. What's the signal transfer function? Yeah, the signal transfer function's a delay. And there's the noise transfer function. So let's sketch VQE of F. And this was VLSB. We'll do it in power over 12 FS. Anybody agree or disagree with that? And then what was the transfer function of 1 minus z to the minus 1? Just, we'll do that. 1 minus z to the minus. Here, let's, instead of me drawing it, why don't I show you, remind you in chapter 1. That is on page 15, right there. Does everybody see how it goes up? So I go back and I go, okay, the noise transfer function looks like this. And it comes back down. And so if I take the intersection of the two, basically what I get is a noise transfer function. I get this whole term that now behaves like this. So, does everybody agree with that? What's that? Oh, I'm not drawing it that accurate, just sketching it. So, does everybody get the point now that if I pass this output, because remember, if I pass this digital output through a digital low-pass filter here, well, now I've pushed all of the quantization noise up to higher frequencies, and I don't have much signal or much quantization noise down here in the lower frequencies. So what I've done is I can then increase the resolution of my data converter by using this technique, and I can get away with a 1-bit quantizer, which has horrible quantization noise. Just use a high oversampling ratio and push the quantization noise to higher frequencies so it can be filtered out. Does everybody follow that? Okay, so this is a key point, because when we talk about noise shaping or delta sigma or sigma delta topologies, they don't reduce the quantization noise by using a high resolution quantizer. What they do instead is they push the quantization noise to frequencies outside the bands of interest so that you can remove it with a digital filter. And same thing with bandpass. We push the noise out away from the band, or the IQ signals we're trying to demodulate, and then we filter it and get rid of the quantization noise. And I want to go through, we're going to start in chapter 6 right now. I put some other stuff in the last section there in chapter 5 on predictive and noise shaping and all that. It's only like 2 pages to read, so I'd suggest you read that. But when we start chapter 6, what I'm going to do is I'm going to go through some real simple examples qualitatively, because this gets really mathematical really fast, but it's really simple stuff once you understand. The math looks complicated, but it's not. So let's go ahead and pause here, and then we'll start chapter 6.